Okay, here we go. We're going to look over the most recent quiz, and we're going to use Jimmy Haggerty's right here. Thank you, Jimmy, for having an excellent score, and we're going to use yours as the base for comparison. Okay, so here we go. Find the domain of the function. The domain here says, of course, that we're dealing with um, the square root, and whatever under the square root called the radicand must be greater than 0. So setting that up, we get to this point, we end up having to divide by a negative, which calls for a reversal of the sign, and there it is, used as a interval notation. Okay. The second problem, again, a root. So what's underneath the root? This expression here must be greater than or equal to 0, the same as it was in the first one. But that is an expression which is going to require us to use a sign table to determine when it is greater than or equal to 0. So, which means we had to factor the denominator. Some people got that denominator factored incorrectly, therefore it led to wrong results. Then we're going to set up our sign table built around those values on the in the factors of 5 and 5, 1, and 3 halves. Okay, and build our sign table. And from our sign table, we can determine the regions where it's positive. If it goes positives in two regions, stated here 1 comma 3 halves and 5 comma uh, infinity. And again, we made the statement over here that x cannot equal 5 or 1, so therefore they were not bracketed, whereas the 3 halves was bracketed. Okay. Um, this is the cube root of that same function, and so we can take the cube root of anything, but okay, we can't have a 0 in the denominator, so we have to adhere to the restrictions of the denominator not going to 0. We don't have to worry about whether the entire fraction goes positive or negative, just as long as the denominator doesn't 0 out, which is all values except 5 or 1, but stated in interval form would be as stated here, negative infinity to 1, 1 to 5, and 5 on out. Okay. Um, Here we're needing to find the range of the function. Okay, in order to find the range, let's back up. We can find the domain because we know what x can't equal in the denominator. If we can get y in the denominator, then we can determine what y can't equal. So what we do is we call our function, since our function f of x is another name for y, so we put y in here. And invariably now what we want to do is switch this up so that x is over here by itself and y is over on the right hand side. So we're going to cross multiply. Y times x minus 1 equals 2x minus 3. You're going to distribute your y. And then from here, it looks like it got cut off, so let me finish it up for you. So from here, we're going to switch out our terms here so that I can collect the x terms on one side. So I get x, y minus 2x is equal to y minus 3. That's just collecting my x terms to one side. And that doing that, then I pull out x and I get y minus 2, okay, equals y minus 3. And now I can solve this for x. So x is equal to, just as Jimmy is showing us here, y minus 3 over x minus 2. X can't equal, I'm sorry, y minus 2 over y minus 3 over y minus 2. Okay? And y can't equal 2, so therefore the range is everything but 2. Okay. The next page asks us to do some evaluations. Okay. Just plug this value in, do the computation, 38. F of negative 4 over 3 times g of 11. So it's just a matter of plugging in negative 4 into the numerator, and that ends up giving you negative 15, and plugging in 11 into the denominator expression, which then multiply by 3 and simplifying it. Okay, this is just a evaluating this, which says replace the x with x plus 2, take its opposite, and add 1, and that's basically all you had to do. Okay, which gave you all this, and that wasn't even necessary that you expand it that way. This was certainly sufficient. Okay. Um, Find all values of x for which the function equals 0, which means you're simply solving this equation, which is factorable in 5/2 and -3 of our solutions. And here, this at the point was given was a little sneak preview of what we are doing now. Okay. And there's Mr. Non telling us that the next shuttle is leaving in 10 minutes, so you better get on it. All right. So here we are back at this. This is testing to see if you could grasp this concept. Okay. And this is now exactly what we call a composition. At that point, we didn't know it, but that's okay. You should understand the notation that says in function f, replace all x's with g of x. Okay, so there you go with that. This down here was asking all questions about some of your basic functions. It was a good thing, as you can see, what Jimmy did was to write, just do a little sketch of each of the graphs, noted the restrictions in the domain and the range, okay, uh, and went through which has the domain from negative infinity to positive infinity, uh, absolute value of x, and okay, the x cubed, which has a range from 0 to infinity, okay, which is absolute value of x and square root of x, which has a domain the same as the range, okay, or not a, because that's the range is only positive, domain is all, right? Here, yes, because they can't have x equaling 0 and can't have y equals 0, so that's the same domain as range. This is for all non-negatives, okay? So that's for both domain and range, and this is all numbers both in domain and range, okay? So B, C, and D is a function for which this is true. I think that most of you didn't know what that meant when it said that. What it says is when I replace x with its opposite, there's no change in the function, okay? Which is the function, which means what happens when we replace x with its opposite, okay? Where we are reflecting across the y-axis. So this says reflected across the y-axis, and there's no difference, okay? Which is characteristic of what we call a stupid function, of which x squared is one, but of the ones we select here, of the ones we offer, absolute x is the only one. And this other thing here, okay, asks, in which function is it true that if you flip it across the x-axis, flip it across the y-axis, it's the same as when you flip it across the x-axis. That's what this is. When we replaced in the previous, when we replaced x with its opposite, it flipped it across y. When we replace y with its opposite, it flips it across x. So this is asking which ones can you flip across x and give the same effect as if you flipped it across y. And that's any function symmetric with respect to the origin, which is 1 over x, x cubed, and the cube root of x. But I didn't offer you cube root of x, so it's b and d. Okay? Name that graph. Little problems with name that graph. That was a little problems with name that graph. So let's take a look at name that graph. Okay? Obviously, this is a square root function. I have to account for what's being done to it and the sequence with which it's being done. It's been flipped on both x and y and shifted in both x and y. When you have all those things going, we said you should always do what pertains to x first. So I start with the root x. I flip it across the x, which is to take the opposite of the function, puts the negative out in front. Then I shift it in x, and it looks like it shifted 3 units to the right, so under the radical is the expression x minus 3. Now I flip that across the y-axis, okay? I flip that across the y-axis, which means I have to negate that x minus 3 with that sign down there. Lastly, okay, and what happened here is Jimmy distributed that and had a positive right there. And then lastly, you shift it so you get this as your final function. A lot of people had negative signs down here. Look at this. This says if x equals 0, okay, I have a y-intercept, which is the square root of 3, the opposite, add 2, so there it is. if people had this expression under the radical x minus 3, when x equals 0, I'm forced to take a square root of a negative, which has no solution, which would say my graph would have no y-intercept. So it'd be maybe like this. It wouldn't have a y-intercept. So that's why I've said to you, you need to check those things. Okay. This shouldn't have been too bad. X squared has been flipped on the x, so I put the negative out in front. I shift it, okay, which is to the right, so that's x minus 3, and then I move it down. So there's my final on that, okay. This is, I mean, people didn't even have the right function here. It's x cubed. You can't get x cubed and the cube root of x confused. They're two entirely different functions. Please, x cubed is the graph as was shown here initially positioned. X cubed, if you flipped it on x or y, makes no difference. So I get it done first. Flip it on x. How do we account for flipping it on x? With that negative sign out in front. Then we shift it. Okay, it looks like it's been shifted to the left, so it's x plus 3, quantity cubed, negative out front. Then you shift it up 2, and there you have it. Okay. Here we're back to another square root graph. Okay, here's the square root of x. Okay, this says move it 4 units and then flip it on y. Okay, so I moved it 4 units. Okay, I flip it on y, and I'm sorry, I'm not flipping it on y, I'm flipping it on x. Okay, no, flipping it on y, I'm sorry. So flipping it on y here means negate all my x terms here, okay, and then I'm going to shift it in y. And again, look, this thing does have a y-intercept, okay. If I kept that as negative, see, as Jimmy distributed it negative there, that's fine, okay. Uh, if you again had this something under there like x minus 4, that's asking you to find the square root of a negative, which is imaginary, and the graphical impact would be that it have no y-intercept, which in fact it does. Okay, name piecewise graphs down here. Okay, this is a line segment, rather a segment. Well, we have 2 points. With those 2 points, we can find the equation of that line, which is 3x minus 2. People just didn't go through and find the equation. 2 points determine the equation of the line. There it is, defined between -2 and -1. Okay. This is the unit circle, quarter, which is root 1 minus x squared, and then here comes your square root of x taken over. The other one, it's not shown here. I did give you points which would enable you to find that the 2 pieces were 1 over x on one end and 1 over x on the other, and x cubed in between. Okay, people were telling me that these portions in here uh, on the left and the right, extreme left and right, were variations on the square root. I did not take it off if it sounded reasonable, but I did not mean for it to be that complicated. That's why I gave you the points there, so you could determine. Okay, you can see here I give you 2 1/2. Well, that's telling you it's when x is 2, y is 1/2. Okay, it's telling you it's the 1 over x function. So there is your quiz, and of course, go over it, make sure you're good with it, and you know all that stuff for the upcoming test. Okay, there you go.